Go, go! Hi, chemistry students. This is your big lesson for whenever. It's time to actually do some chemistry again. And that means learning some stuff and doing some problems. Yep, so you're going to need your book. Hopefully you brought your book home. And we're going to be doing section 10.4 on spontaneity. You probably also, if you've got your periodic table and all that, this thermodynamic data sheet. I've scanned mine. And then the handouts that I gave you for this section, we'll be going through those slides, and we'll also be looking at some of my notes that I took. Your notes should probably end up looking like my notes, because I know how to take notes, because that's my job. Right. So here we go. We're going to look at defining entropy and discuss the factors that influence the signs and magnitude of entropy given the symbol delta S, change in entropy for a chemical reaction. We're going to have another symbol, and that'll be delta G. That'll be for Gibbs Energy, a scientist who wanted to know the total available energy for a reaction. And then we're going to have one really important equation. Delta G equals delta H minus T delta S. We'll see that in a little while. You'll see it later in your section. And that is the equation that will help us determine whether a reaction is spontaneous or not. Whether you just pour the things together, they'll react, or whether you put two things together and nothing happens for a while. So that's the plan. And so let's get into it. So I'm asking you to put your thinking cap on today. I know I don't have thinking cap on, but I gotta let the heat out. So, yeah, stupid joke, Dad. Okay, whatever. All right, here we go. Describe. What slide am I on? Okay, let's go to this slide. Can I do that? Thank you. Right. Okay, so let's first define entropy. If you want some bonus points, you can go and watch the 60 symbols video on entropy. Got a guy on there called Dr. Moriarty, and I'm serious, that's his name, is Dr. Moriarty. He describes what entropy is like from a physicist's point of view. Entropy is basically when things get a little crazy. Okay, we can see here on the screen, sort of, you can see on the screen. Some reactions happen easily, but others don't. If you bring sodium and chlorine together, they will react. But nitrogen and oxygen hang out in the air together and they don't react. You need special conditions for them to react to form nitrogen monoxide. So one of the factors that we use to determine whether a reaction is going to happen right away or whether you have to do stuff to it, like raise the temperature or stir it up or break it up into pieces or turn it into gas, is to see if there's a decrease in enthalpy or delta H, if that is negative. Entropy kind of plays into that. Entropy is kind of the disorderliness of a system. Entropy measures disorder and is a thermodynamic property. In fact, if you look at that, we have thermodynamic data. This column here with delta S, those are all values for entropies. And note they're in joules per mole kelvins. So it's a certain amount of energy here is what we're talking about for every mole, and depends on the temperature that we're at as well. So entropy, disorder. You can see in your book there's a picture of them putting some potassium permanganate, which is a powder, into the water, and it slowly dissipates, it slowly dissolves, which is an increase in entropy when something dissolves and goes around all over the place. So we're looking for more chaotic systems are going to be more able to react right away. If something's very stable and like a solid crystal or something like that, it's probably not going to react very quickly. But if you have two gases, they'll react very quickly in general. Entropy is not a form of energy, but it does describe energy. A process is more likely to occur if you get a big amount, well, just an increase in entropy. If entropy goes up in a reaction, then you're probably going to have the reaction occur spontaneously. So we're looking at describing entropy as delta S. That needs to be a positive. Factors that affect that. Well, hang on. Let me go to my other stuff here. There's our entropy stuff. You might want to pause and write that stuff down because that's what I wrote down from the notes. Okay, so we want that. We want delta H to be negative. We want delta S to be positive. It'll make more sense when I show you the equation. Kind of nice doing this way, huh? At least I'm out of my pajamas. But here we want to just kind of start making a list of factors that affect entropy. Factors that affect entropy. And I got a quick list here. Here's my summary, my distillation of some of the stuff in this section on entropy. Is that you can see in the picture with the potassium permanganate that dispersion or dissolving something increases its entropy. So now it's all spread out, and it can interact more easily if it's floating around there in water than it could as a powder. Diffusion, and that would be with gases. You spray a gas and it's right here and it spreads out throughout the whole room. That's one way that you can increase the disorder of a system. It's not all in one place. You can't really control it, and now it's all over the place. So dilution, diffusion, okay. If you want to dilute something more, add more water to it, spreads it out even more by concentration. So that's way that will change your entropy. If you reduce the pressure on a gas and allow it to expand, that's going to change the entropy. I think if you got higher pressure, that's going to make it more likely that a reaction occurs. Many reactions in labs, they do it under certain pressure conditions. So that's one thing. You can add more particles, and that'll make things a little bit more chaotic. More things to try to handle. It's like juggling. Juggling 2 is not so bad. Juggling 3 is certainly a different thing, and juggling 4, I can't even do that. So if we add particles to a system, that's going to increase its unpredictability, we could say, or its disorder. What else have we got here? How about this one? Reactions that produce more gas particles. So you look at the states of matter in a reaction, and if it's supposed to create gases, that's something that will change the entropy. Gases are more unordered than liquids are, which are more unordered than solids are. So if we go up the scale of states of matter, we'll get higher amounts of entropy. If you look at the top of 359, you get a table there of standard entropy changes for some reactions, and I think I also have that on the PowerPoint here. Okay. Here's basically the bullet points for what I was just describing in my notes. Entropy can change during the reaction. Entropy can increase when you change the number of things that are in there. You can tip that thing by adding more of one thing than the other. Entropy can increase in a system when the total number of particles in the system increases, and entropy also increases when a reaction produces more gas particles. Okay, let's go to the next one. We got here some examples, and the main example here is of salt formation, like table salt formation. That's what we're talking about. And you can see here that you've got sodium and you got chlorine, and sodium is a solid and chlorine is a gas, and you want to produce sodium chloride. You can see over here that if our change of entropy from the reactants to the products is a negative, this thing has now actually become more stable in the process. We can bring these two things together. They're fairly unstable, and so they react with each other, and then they form a crystal, right? They form a solid, and that's much more systematized. It's much more orderly than the solid and the gas, chlorine gas being pretty crazy stuff. So the decrease in entropy happens because the order present in crystalline sodium chloride now is in there in the products. Now, this right here, this reaction that you see here is when you put salt into water and you stir, all right? You take some solid crystals and you drop it in the water and you stir it until they break up into small pieces and float around inside of that water. Okay, the entropy increases when a mole of sodium chloride dissolves in water to form a mole of aqueous solution ions and a mole of aqueous chlorine ions. All right, so you see here, delta S goes up. It's a positive 43 joules per Kelvin if we're doing this in moles. Obviously more chaotic if you take that thing and it dissolves and spreads out in smaller pieces. Order is lost. There's the crystal structure breaks down and you get the ions that are floating around separately and not staying in their kind of regular structure. So this is the same chart as you've got there in the book. Again, scientists have already done a lot of the measurements of these things. They've done the reactions, and they've measured befores and afters, and they're able to find out how much the entropy changed in the reaction. As you can see, we've got a few of them that have positive entropies. That is, that they get more chaotic, which probably means they're less likely to happen. And then you got these negative ones here, which to me it looks like all you need to do is just bump it a little bit and those reactions will occur. From beginning to end, they actually become more ordered rather than less ordered. The top ones, positive entropies, they become less ordered. The bottom ones here become more ordered. So you look at the type of reactions we got here. This is the dissolution of salt right here, 43. This is taking nitrogen gas and oxygen gas, which are present in the air, and making nitrogen monoxide. Well, that doesn't normally happen, does it? So we're doing something to this to get it to occur. Its entropy increases. It gets more chaotic. This is gasoline. Well, it's methane and oxygen combusting. Well, that becomes more ordered. Carbon dioxide as a gas and H2O as a gas is better than having CH4, and especially CH4, because you know if you've ever gone to the gas station and filled it up, you can smell the vapors. They're becoming, going from liquid to gas. They're becoming more disordered there in that process. So we're bringing more order to it by combusting, and we can collect the carbon dioxide and collect the gas in a more ordered form. Here we get the formation of salt, which goes from more chaos to less chaos. And here we have a reaction that goes from more chaos to less chaos, more stable form into O4. So again, you look these things up on a chart to find how much the entropies have changed from beginning to end. And what we got here then is a summary of some of the things that we're going to want to keep in mind as far as what changes and what if this makes this reaction more possible or not. This equation up here at the top is a super important equation. Okay, the little zero thing means a formation. So we're going to have this thing called Gibbs energy, delta G equals delta H, which is enthalpy, change in enthalpy, minus this quantity here, the temperature that the reaction is occurring, and delta S, change in entropy. And this would be a good place to pause and copy that chart down. And we'll be talking about it a little bit later. It'll say if the values are positive or negative, if delta G will be positive or negative. And then that we're going to use that as a grid to determine whether something's spontaneous or not. So go ahead and pause, copy that down. Okay, folks, I'm going to go back over to my notes, make sure that I've covered everything we need to. Okay, Hess's law comes next. Hess's law was that thing where we just look at the before and after and we find the difference between, I guess originally with Hess's law we were looking at enthalpies of the products minus the enthalpies of the reactants to get our change in enthalpies. We're going to do the same type of thing with entropy. We're going to look at the entropy before and entropy after, and then work the numbers and see if the entropy went up or if it went down. Green tea fights off coronavirus. So that would be page 360 in your book, and it's got the picture of the touch powder thing. Remember the video that we watched in class? Um, so Hess's law applies to that. Remember that reaction only needed just like a bump, like you could actually knock the stuff or step on it and the stuff would go off. So here's the way that it works, and I believe this is sample problem. This is sample problem F in your book. Hess's law on entropy. And so again, we're going to pull numbers off of this thermodynamic data sheet here. It has both compounds and elements in different states of matter. So I want to show you really quickly where these numbers come from. So they've got the chemical formula where we're doing this in halvesies because this is part of some bigger process. And what we do here is we're going to collect up the amount of entropy in the reactants and the amount of entropy in the products, and we're gonna compare the two. So we've got hydrogen, carbon dioxide, we've got water, and carbon monoxide. All right, so we go to our thermodynamic data here, and we go and we find H2. Okay, we got H2. Where is it? Oh, there it is. Nope, that's Hg. Hg, H2. Where is H2? Oh, I'm looking in. What column am I looking for? Here it is over in the second column, which you probably already saw because you have young eyes. Okay, and we go over here and we're like 130.7. There's our S, our entropy for that stuff to occur. And then our other ones were carbon dioxide. So we got that over here. Where do we have it? There it is. Carbon dioxide as a gas, 213.8. We've got water. Okay, so you got H2O as a liquid or as a gas. In our particular problem, it was a gas, so we'd use the 188.7. And carbon monoxide as a gas, there's our 197.6. Okay, so that's where these numbers come from, and we collect up on this side. We got half of this and half of that. That adds up total of 172.25 joules per Kelvin of entropy. And then on this side, these two add up to 193.15. That's a change, a positive change, 20.9 joules per Kelvin. This thing becomes more disordered as that reaction occurs. I'll show you the first practice problem here as well. Carbon monoxide, there's the same number that we see on the chart. We got H2, which is the same as this one. And in this reaction, we have one of these. We have 2 moles of these, and we have 1 mole of the methanol. Okay, so we add these two together, twice of this because we have 2 moles of hydrogen. We get 458.4 joules per Kelvin on the left side, and we end up with 126.8 on the right. That is a decrease in entropy of negative 331.6. Those ones are pretty straightforward. They're very similar to the other ones. I think actually they're easier than the other ones. And I did it this way rather than that whole entropy of the products minus entropy of the reactants. It's still the change. And I think this way we can kind of see, yeah, it went up, or yes, it went down. And it's kind of easy to figure those things out. Okay, skip down to here, then to this Gibbs Energy stuff. I'm going to go back to the PowerPoint. And we'll scroll down until we get to some Gibbs Energy business. All right, we already described that. Yep, that's the other way we could do it. Standard entropies of some substances. We had more. There's our sample problem. Blah, blah, blah. Okay. Gibbs Energy. Gibbs. Not Barry Gibbs. Okay, page 362 in your book. You got there an avalanche. Anything that says valanche in it is pretty scary, isn't it? Like if you said a chocolanche, that would be pretty scary. Or a cubalanche. Yeah, I don't know. Sounds scary to me. Josiah Willard Gibbs, professor at Yale University. answered the question of what happens when different values of delta H and delta S are positive or negative. Is that going to make something more likely to occur or less likely to occur spontaneously? And so he came up with this thing called Gibbs Energy, which is measuring the total amount of usable energy that you've got for a reaction. Sometimes you got energy there, but it's not in a usable form. So he wanted to know, how do we calculate that, and how that tells us whether or not something will be spontaneous or not. And if you've got available energy, a reaction can probably happen, right? If you don't have available energy, well, then probably something won't happen. So we're looking at the tendency for a reaction to occur depending on both delta H and delta S in that equation. Delta G equals delta H minus T delta S. And we start thinking through the steps of that, right? We're going to think about how that's going to work. So I've got here that if in Gibbs Energy's equation, if delta H is negative and delta S is positive, the reaction is likely to occur. The only other factor is at which temperature that you're doing the thing. And pretty much you'd have to do it at a really, really low temperature. You have to be like close to 0 Kelvin for this reaction not to occur, not to be likely to occur. If delta H is positive, if your enthalpy is positive and your change in entropy is negative, then the reaction just won't. It just won't occur. And the reason for that is you're subtracting temperature times delta S. The temperatures are all going to be positive values because we're in kelvins. So you're subtracting T times delta S. If delta S is negative, you're going minus a negative value. That's adding. That means your delta H is also positive. The second part of the equation is positive. You're going to get a positive answer. Positive answers there. Reaction will not occur. The other cases, if H is positive and delta S is positive, we're not sure. It depends. And if they're both negative, it also depends. So we've got some things to think about here with this type of equation. So Gibbs energy then is the energy of a system that is available to do some work. It's also known as free energy. And there's the equation, though if we're going to measure from beginning to end, we're going to have delta H and we're going to have delta S. Okay? And that information should be given to you in a problem. This kind of looks like, oh, what was I thinking it was like? It's kind of like when you're doing the quadratic equation and you have the part underneath the square root sign where it's b squared minus 4ac. It's very similar to that setup. If your b in front is big, then the other ones have to be big in order to make it negative, right? It can be negative, it could be 0, or it could be positive with the discriminant. That's what that part's called, a formula. So Gibbs energy, also we look at 3 cases. Is it negative when we're all done doing the calculations? If so, then the reaction is spontaneous. It'll happen when you put the 2 things together. Is change in Gibbs energy positive? Well, then it's non-spontaneous. And is the change in Gibbs energy 0? That means the thing's at equilibrium. It just needs to be shoved one way or the other. Like, for instance, if it's 0 and you increase the temperature, then there's less available energy. You're increasing the TS part. If you decrease the temperature, well, then you're subtracting less, and maybe the reaction can happen. So it all just depends on the other pieces here. But we're looking for an answer for G that's either positive, negative, positive, or 0. Negative means it's spontaneous. Positive means it's not spontaneous. And answer of 0 means you're right on the border. Actually, you're going to have probably like a phase change right there. So, yeah. Whoosh. Figure 14 shows them doing potassium and water in a spontaneous reaction. We know that those things in group 1 and 2, they hit the water, they blow up. And so we take that and we look at the answers, the numbers for these things. There is a change in enthalpy of negative 392 kilojoules. Now what does that mean? That means this is an exothermic reaction. Energy is going out of the substances into the surroundings. That's like an explosion there. And then delta S is the change in entropy, the chaos of the system, and it's not very much. But we're doing this at room temperature. Okay, so we've got a negative here for delta H because it's blowing up, but then we're subtracting our regular room temperature, 298.15 Kelvin times 0.047, and overall this gives us a negative, and then we're taking away even more. So that's definitely spontaneous. These are in kilojoules, these are in joules. We'd move that decimal place over here and go 47 times 298, and we're taking that away from a negative 392. So we're definitely going to have some spontaneity there. You can see this kilojoule thing is way bigger. You're going to get some serious energy out here. So the negative again tells us spontaneous. And again, you're going to get a whole list of these things here in your thermodynamic data. We're looking for delta G's, and it'll tell you for forming these things. For instance, let's take a gas of some sort here. No, it doesn't do it there. Okay, let's take something else. Carbon dioxide to form, spontaneous, because our delta G is a negative. Anything here that's a negative, it will form spontaneously when you go through a reaction of some sort. Okay, so we've got a way of determining whether reactions will occur. And that's the one we just looked at. So you can calculate delta G's in another way because lists of standard Gibbs energy of formation exist. The standard Gibbs energy of formation is delta G with a 0 in the top and an F down low of a substance is the change in energy that accompanies the formation of a mole of a substance from its elements at room temperature at 298.15 kelvins. And you can see here, this looks like Hess's law. Standard Gibbs energy can be used the same way that we found changes in enthalpy and changes in entropy. So we look at the total change in Gibbs energy for the products minus the total Gibbs energy for the reactants, and we've got the total change in Gibbs energy for the reaction, and then we can see if that's positive or negative or zero. So there's a few standard Gibbs energies at formation, but you've got that whole list there in that table. So there we go. There's our main equation for this section. They're going to give you the information, or you're going to go grab that information off of the chart and plug it into that formula to determine amount of free energy and spontaneity. So here's a sample problem. Given that the changes in enthalpy and entropy are negative 139 kilojoules and a positive 277 joules per Kelvin respectively, so our negative 138 kilojoules is our enthalpy, or our delta H, and our entropy is a positive 277 joules per Kelvin. We'll throw those into the equation, and now they trick us here. They say is it spontaneous at 25 Celsius? Well, 25 Celsius is 298.15 Kelvin. So we've got our three numbers there. We got our delta H, we got our T, and we got our delta S. So there we go. And we can see there, all we got to do is throw that into the equation. Negative 139 kilojoules minus the kelvins and the joules. Now you see here they multiply 298 and 277. How do they get 83? Well, if you note here, they've changed the units to kilojoules, right? So they get 83,000 when you do this multiplication. Then they want kilojoules to be added and subtracted from kilojoules. So we get negative 139 kilojoules minus 83 kilojoules gives us a grand total of negative 222 kilojoules. Our discussion said that if it's negative, this is spontaneous. So we determined then that it's a spontaneous reaction. Here's another one. Delta G for the following water-gas reaction. Do you think if you put carbon and water together, anything's going to happen? I mean, some of this you can just put your thinking cap on, right? And look at what it's actually saying. Solid carbon, like graphite or coal, and you put it in water. Is that going to automatically turn into hydrogen gas and carbon monoxide? I think not. So we'll gather up the information for that off of the chart, off of the table. So delta G for water is negative. For carbon monoxide, it's negative. For the forming of the element hydrogen, there's no energy necessary for that. It occurs naturally out there. Graphite, same thing, because it is an element. There's no amount of energy needed to form it. So we're looking at the total change in the products minus the total change in the reactants. And here's the way that the math works. I think that's pretty clunky. Let's see if I have that in my notes. We can clean that up a bit. Let's go down to our sample problem. There it is. Okay, so I just collected up the bits here. Carbon was 0. Water formation was negative 228. And then we can see here on carbon monoxide, it was negative 137.2. And for hydrogen, it's 0. So we're like, look at this. It goes from negative 228 to negative 137. That is, it's going up. It's getting closer to 0. So our change in Gibbs energy is a positive, a 91.4 kilojoules. If you went the way that they did it in the book, you'd do the reactants minus the products. So you got negative blah, 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 minus negative 228. And that's where you get your positive 91.4 kilojoules. So it's positive. It's non-spontaneous. Now, what would you need to do to get that to actually react? Heat it up. That could be a possibility. You could heat it up. Especially like set the coal on fire. How about that? That might do the job. You get carbon monoxide and hydrogen gas like barbecue, right? How about this one? Carbon and oxygen, carbon to make carbon dioxide. All right, well, that's a different story, isn't it? So now we've got collecting up these things. You've got 0 and 0 and producing negative 394.4. So these are 0 because they're already elements. And now on this side, we're at negative. So the total change there is negative. It's very spontaneous. Very spontaneous. Carbon and oxygen will react with each other. Yeah. Second practice problem, you got calcium carbonate. Will it yield these ones spontaneously or not? So I went to the chart and I go calcium carbonate. You see that anywhere on here? Calcium carbonate, there it is. And we go to our Gibbs energy, there it is, negative 1128.8. And then we got calcium oxide and carbon dioxide. They're on the chart too. Calcium dioxide is right here, negative 604. And carbon dioxide's on the chart as well. I believe it's over here. Yep, negative 394.4. So we pull those numbers off the chart and we compare reactants, products, total change in Gibbs energy on the product side is negative 998. So we went up, didn't we? From that to that. That's a positive. This is non-spontaneous. This is a decomposition reaction. You need to do something to it. We did this. Well, I don't know if you did this, but you just heat it. You just heat it and it breaks down. So chalk won't break down all by itself. That's what this is. But if you heat chalk, then it'll break down into CaO and CO2. And you could tell by just weighing it before and after, because you didn't see the carbon dioxide. You can't weigh it. Okay, so we're almost here at the end. I give you like the best example of thinking about some reaction that's spontaneous, unless you know about some regular reactions. Predicting spontaneity, then, how does temperature affect it? Right? Because temperature is sitting right there in that equation. And so, like if temperature is really big, then if delta S was positive, then you're going to be subtracting a big number. Okay, you're going to be subtracting an even bigger number if you increase the temperature. So you want to think about that. if the temperature ends up being high enough, it can make a high enthalpy, low entropy reaction occur. Something that wouldn't normally occur given delta H and delta S off the charts. If you ramp up that temperature, you can make it so that it does occur. You can tip the balance by just raising the temperature on a reaction. And a good example of that is photosynthesis. Photosynthesis doesn't happen at night, which means it's not spontaneous. And so you think, what's the difference between night and day? It's not that you're asleep or you're awake. It's that there's sunlight and that the temperature warms up during the day. So there needs to be a certain amount of energy that's available, both temperature-wise and just light energy that's going to warm up the chlorophyll and whatnot inside that leaf. So it needs light energy to fuel this problem, and it does actually convert kind of to heat, but that's its energy source. So we take our very common thing for photosynthesis. This is not like the balanced equation for regular photosynthesis, but this will work for our example here. If we were to go grab the change in Gibbs for this and this, compare it to this and this, we would not be able to do this spontaneously. We need to up that from like 298 to higher. So we get a total change in H of 2,870 kilojoules per mole. That is a pretty big number. We probably need a little bit more something else on the other side. We need a little bit of sunlight to give us enough energy for this reaction to happen spontaneously. See if we got that in here with thermodynamics. All right, let me back up here. There's our equation again. The term delta H and delta S change very little as temperature changes. The presence of temperature in the equation indicates the temperature may greatly affect the change in Gibbs. And then by consequence, spontaneity. Suppose a reaction is both positive delta H and a positive delta S values, which is one of the cases that we already looked at. Now temperature really does matter. If a reaction occurs at a low temperature, the value for T delta S will be small and will have little impact on the value of delta G, and we'll be subtracting a very small amount. The value of delta G will be similar to the value of delta H and will have a positive value. When the same reaction proceeds at a high enough temperature, T delta S will be larger than delta H, and delta G will be negative. So what that's saying is raise the temperature, right? Now the part that you're subtracting, the T delta S will be big. It'll be bigger than the delta H, and now you've tipped the balance so that the delta G ends up being negative, and that means that the reaction is spontaneous. So increasing the temperature can make a non-spontaneous reaction spontaneous. Non-spontaneous reactions cannot occur unless some form of energy is added to the system. All right. Now, that's the understanding concept, so that's pretty much done. I will probably make another video here that will, yeah, I don't know. We'll see. But there you go. There's our lesson thing. I'll pump out an email letting you know which problems I'd like you to work on, stuff for the next round. But, yeah, this is pretty much what you need to have for Monday. And then probably on Monday we'll be doing some practice problems with this stuff. Maybe we'll do the end of the chapter business, but there's no test on chapter 10, so we'll be shifting gears and we'll move right into chapter 11, which is more of the same type of stuff. We're going to do phase changes, I think, in that chapter, and have heating curves and things like that. So stay tuned for that. I will let you know by email what else is required to you, but you guys need to make sure that you're taking care of your work because you are still in school. You need to make sure that you took good notes on this and that maybe you could write on your slides if you wanted to or whatever, but the next round is going to be doing some practice problems of your own and finishing up the chapter. So there you go. Thanks for tuning in, and we'll see you from another secret location later.